Hey everyone, welcome to the notes on areas of regular polygons and composite figures. So a regular polygon means that all the sides and all the angles are congruent, and so we're going to be able to find the area of polygons that are regular. And a composite figure is like if you take a square and then like right next to it attach a half circle or attach a triangle. It's two or more figures that are kind of back to back spliced together. So let's begin with some vocab terms here. In the figure, a regular polygon is inscribed in circle P, meaning all of its vertices are on the circle. The circle is on the outside, the polygon's inside, and circle P is circumscribed, so that's what goes around it. The center of the polygon and the radius of a polygon are also the center and radius of the circumscribed circle. So where that is in this picture is right here. The center is P, and from P to any point on the polygon, to any vertex on the polygon, that's the radius, what we call the radius of the polygon, but that's also the radius of the circle. If I was to take that blue segment that I just highlighted and, swing it around the whole circle, that's going to be the circle in question. Okay, now the next part here is the apothem or the apothem, depending who you're talking to. But the apothem is a segment that's drawn perpendicular to the side of a regular polygon. So here, right in this picture, this is the apothem or apothem. Sorry about that bell. Okay, so it's perpendicular to the side. So if this shape, for example, we have a regular pentagon, it would have 5 of those. It also has 5 radii. The circle has an infinite amount of radii, but the pentagon here would have 5. So another thing to note here is the length of the apothem is the height of an isosceles triangle that has 2 radii as legs. So let me draw that in. If I was to, so these are the radii, so they're congruent. That's an isosceles triangle for sure. And then when you draw in that apothem, that is the height of that triangle. Remember, every triangle has 3 heights, but that's one of them. That's from the vertex angle. Sorry, I realized from your end that didn't get drawn in. So here's where we're talking. This right here is the isosceles triangle. Both of these segments are the radii, so they're congruent. That's our isosceles triangle there. And so then this segment is the height of the triangle, which is AKA the apothem. All right, so this next little piece here is about the central angle of a regular polygon. It has its vertex at the center of the polygon, and its sides pass through the consecutive vertices of the polygon. So what we're talking about here, let me erase these things that I drew. So the angle that we're talking about is right here. Okay, and so every polygon, if I was to draw this central angle here, there's another one here, another one here, and another one here. If I was to take this angle plus this angle plus this angle plus this angle plus this angle, that's going to add up to 360 degrees because it's a full circle. And then we would divide by, in this case, 5, because these are all going to be congruent. This angle, they're all the same measure. So in this case, we would divide by 5, but normally that's just going to be dividing by n, the number of sides in the polygon. All right, so now, first example, in the figure, regular hexagon JKLMNP is inscribed in circle R. We're going to name the following: the center, the radius, apothem, and a central angle, and its measure we're going to find. So the center here is just R. The center of the polygon is the same as the center of the circumscribed circle. Radius, well, there's a bunch of them. 2 of them are drawn here because it's always from the center to any vertex of the polygon. So we have 2 that are drawn. But we also have all of these that are not drawn. So all of those answers are correct. So from R to any vertex of the polygon would be perfectly acceptable to answer. So I can say that it's RK, RL, whatever. KR, KL, all of those are fine, and those are segments because it's a radius. The apothem is right here, RS, and then the central angle is going to be 360 divided by the number of sides here, which is 6, so we get 60 degrees for the central angle. All right, so now we're going to talk about how we can find the area of a regular polygon, which has n sides, by dividing it into n number of congruent triangles. So what we're going to do this area is we're going to take the area of one of these triangles and then multiply by the number of triangles in this shape. So like here, if we're looking at this triangle and we find that area, we're going to multiply by 5. So if you were to look at this formula of where it comes from, the base times the height times the number of triangles, 1/2 times that. So the base we call S, the height is the height of the apothem, it's A, and then times N. But I don't even like to think of the formula. I just like to think I'm going to find the area of a triangle, and then I'm simply going to multiply by how many triangles there are. I'll show you in the next example. All right, so let's do some examples and put this into motion. So here we're going to be finding the area of each regular polygon. It's important that they are regular, otherwise we can't do this. So I always like to draw or redraw the one triangle that I'm going to be focused on for a problem, and in this case it's going to be QPR. Then we know that PR is 10 inches, and this is the height of the triangle drawn in there. So typically the first thing you want to do is find the central angle, because then we're going to have some more information about this triangle, because right now we only know one side. So remember, if I was to split this up, there are 5 of them. The angles add up to 360. So the central angle is going to be 360 divided by 5. So that gives me 72 degrees. So this angle up here, angle P, is 72 degrees. The next thing I'm going to do is just decide how am I going to find the area of this triangle. Remember that the area of a triangle is 1/2 base times height, or what I can do is also use that formula from last week where it was 1/2, and then if you have 2 sides, it'd be A times, let's say you have side A and B, and then sine of angle C. And so it's just completely up to you how you want to do that. Now this triangle, if I wanted to, I could drop this altitude, call this the base, this is the height, use trig. If this is 72, if I split it in half, this is a 36-degree angle, and I have the hypotenuse, so I would use sine, and I would use cosine to get the height and the base. But I'm going to go this route for this one, because if this is 10, and that's a radius, this is also 10. So I know then that the area of this triangle is 1/2 10 times 10 times the angle, sine of the angle between them. But remember, we don't want the area of the triangle necessarily. We want the area of the pentagon. So we have a 5-sided figure here. So what I would do, this right here is the area of this triangle. I would find that entire area. So how many of those triangles are there? There's 5, so it's going to be 5 times 1/2 times 10 times 10 times the sine of 72. This number in front here is always going to be the number of sides. Now, one thing I will mention, had I found the area of this triangle by doing SOHCAHTOA, then it would have to be 2 times n would be in front, because these right triangles, it takes 2 to create the big one that I have here. So type that into your calculator, and we get an answer of approximately 237.76 inches squared. Okay, this next one, again, I like to redraw my one triangle. If the triangle is not drawn in the picture, I just always know I have to go, the radii of it and then draw that. So we have A, B, C. Drop the height down. This entire length is 3. So that means when I drop the height down, I break it up into 1.5 and a 1.5. First thing I'm going to do, find the central angle. That's going to be 360 divided by the number of sides. In this case, we have 6. That's 60 degrees. So because this is 60 degrees, and I know that this is an isosceles triangle this way, these two angles have 120 degrees left over for them to share equally. So what we have here is an equilateral triangle. So if this side was 3, this is 3, and this is 3. And I could use our little shortcut formula. So let's find the area of one triangle. It's 1/2 That's a 3. 1/2 3 times the sine of 50 degrees, 60 degrees. Jeez. And so that's going to give me the triangle. I want the area of the hexagon. So I'm going to do 6 times 1/2 times 3 times 3 times the sine of 60. Type that into my calculator. Now get the approximate area. It is 23.38 meters squared. I'm going to do this another way just because you're not always going to be able to use that formula. Let's focus on this triangle one more time. And when I broke it up, and this was 1.5, I know that this little angle, when I split it in half, is 30 degrees. So this is a 30, 60, 90. So it's L for the short leg, L root 3 for the long leg, which in our case is the height, and then 2L for the L root 3 and L over here. So I can find the height of this triangle. It is 1.5 square root of 3. So to find the area of one triangle, it's 1/2. The entire base here is 3 times the height we just found is 1.5 root 3. So if I was to simplify this and then multiply by 6, so I do 6 times 1/2 times 3 times 1.5 root 3, I would get the exact answer as 13.5 root 3, which is exactly what we got up there, 23.38 meters squared. So for these problems, really what you have to do is any means it takes, because there's different ways to find the area of a triangle, and then multiply it by the number of sides. That's how you get the area of a regular polygon. Number of sides times the area of one triangle. Or this, sometimes if you do little right triangles, is 2 times n. Okay? All right, the last piece of notes here is areas of composite figures. A composite figure is a figure that can be separated into regions that are basic figures, such as triangles, rectangles, trapezoids, and circles. To find the area of a composite figure, find the area of each basic figure, and then use the area addition postulate. So looking at this first picture, and you get a little bit better as you practice these, but I see that we're going to have a triangle, and then we have a rectangle in the middle, and then we have a half circle. So I want to find the area of this region plus this region plus the third region if I was to number these 1, 2, and 3. Okay, and then I like to write my little formulas underneath. The first region is a triangle, so it's 1/2 base times height, plus rectangle is length times width, plus a circle is pi r squared, but we have half a circle, so it's 1/2 pi r squared, or pi r squared over 2 is the same thing. Okay, so I see that I have to find the height because I'm missing it for the triangle. So right now I have a right triangle where I only have the hypotenuse. That means I need to find, I don't have anything here, anywhere in these pictures, in this picture that gives me this height. So clearly I'm going to use that this is 22 and this entire distance down here is 31. Well, if this is 22, this is 22 as well. So to find this leftover piece, that's the leg of my triangle, I'm going to do 31 minus 22, so I get 9. So now I would do Pythagorean theorem for this triangle. I'm going to do 9 squared plus h squared equals 15 squared. Some of you may notice this is a triple. So 81 plus h squared equals 225. And if you notice it's a triple, you can just do this quickly. We end up with the height being 12. Okay, so far I have 1/2 9 times 12. Plus, well, the rectangle, the length is 22, right? This is the length up here. Times the width is the height that I just found, so 12, plus 1/2 pi, I need the radius of the circle. This diameter is the same height as what we got on the left side for the triangle. It's 12, so the radius is 6. So it's 1/2 6 squared. Okay, let's clean this up. We would get 54 plus 22 times 12 is 264 plus half of pi times 36 is going to be 18 pi. Half of 36 is 18. Putting the things that I can combine together, I can combine my constants, 54 and 264, add those together, and I would get 318 plus 18 pi. Okay, and that's my final answer for this problem. Next. Well, here we could break this up into maybe 2 trapezoids if we want, but I'm going to go about this a different way. To find the area of the shaded region, I'm going to find the area of the rectangle minus the area I don't want, which is the area of the triangle. So the area of the rectangle, length times width, minus the area of the triangle is 1/2 base times height. Okay, the base of my triangle, 6. It's the same as for the rectangle. The height is in here. So how am I going to find that height? Well, by dropping that height in, I've split this into 2 equal pieces. This is the height. I'm going to do Pythagorean theorem here. So it's going to be 3 squared plus h squared equals 4 squared. So 9 plus h squared equals 16. Subtract 9 from both sides, you get h squared equals 7. So h is equal to the square root of 7. All right, so let's go ahead. 5 is the length times the width, 6, minus 1/2. The base of the triangle is 6. The height we had to go and find, it's the square root of 7. 5 times 6 is 30, minus half of 6 is 3 square roots of 7, and my units are meters squared. And that's my exact answer. All right, that's it for these notes. We'll practice this in class tomorrow because it takes a little bit maybe getting used to the pattern of how to solve the areas of a regular polygon, but then kids get really, really good at it. And you're going to be able to use special right triangles sometimes, SOHCAHTOA sometimes, that secret, side times the sine of the angle formula. It just depends from problem to problem. All right, thank you so much for watching. Have a good one. Bye.